Hello everyone, a warm welcome to the second week of eSchool on climate science and policy. Those who could not attend the previous sessions can find them on the YouTube channel. Kindly ask your questions in the link provided below in the description. Today we have with us Professor Eswar Rajasekaran. Dr. Eswar is working as assistant professor in the Department of Civil Engineering and IDPCS. He had done his doctorate from IISc Bangalore with the theme of remote sensing applications in modeling land surface fluxes. After this, he worked as a postdoctoral research fellow in NASA Jet Propulsion Laboratory, California, USA, for about 2 years. Dr. Ishwar's research interests include thermal infrared remote sensing and its application in water resources, vegetation monitoring, and drought monitoring. We welcome you, Professor. Today, he'll be discussing about the topic remote sensing for climate studies.
Thank you for a nice introduction, and thanks for the opportunity for me to discuss my lecture here. And anyway, good evening to all of you. Welcome to this particular lecture, remote sensing for climate or earth system studies. Originally, the topic I proposed was remote sensing for climate studies, basically, but later I thought remote sensing is not only limited to climate system, but now being used for earth system as a whole. So that's why I changed the topic a little bit, and we will get on to the discussion. Before we go on, there's a small spoiler alert. The contents of the talk will be extremely basic, and I'll be touching only upon the fundamentals of remote sensing, and we will not be looking at some hi-fi studies and all. So people who are all already working with remote sensing data sets, or who already has like good experience with remote sensing, please pardon me. The idea of my talk is to introduce remote sensing to people who have not used this particular technology for their practical applications. Like last year, when this particular program, like this school was being conducted in live physical mode, I delivered the same lecture, remote sensing for climate studies, that time also. That time, like students were there physically present. I went to the meeting hall, and when I inquired the students that how was the remote sensing background, almost like 80-90% of the attendance replied back with a negative. That is, they don't have any background in remote sensing. So I thought, like, even though remote sensing is like a really advanced technology, most of our students, especially the undergrad and early student and students in the earlier part of like postgraduate studies are not being introduced and not being given full attention to this particular technology. So I thought this can be an eye opener to people who want to use this technology. And any further discussions, like advanced part, if you want to discuss with me, feel free to discuss at the end of this particular lecture. Okay. Before we move on to our core theme of the lecture, I would just like to recall what happened in the previous lectures. Like in the first talk by Professor Subhimal Ghosh in this school, one of the questions asked was how remote sensing is useful for modeling land surface atmosphere interaction. Then when Professor Eldo was talking about hydrological applications of climate studies and different things, he showed a lot of images and maps that were acquired using like remote sensing data. So we might be coming across some of the common problem statements. What is the effect of land use, land cover on stream flow? How our water resources is changing with change in climate or change in land cover patterns? How do we track hurricanes? Basically, we hear news, or some of us might be even doing work to check whether hurricanes are intensifying because of change in climate. Is it really true? How to track hurricanes? And when Professor Subhimal Ghosh talked, he might have talked about like effect of large-scale irrigation on monsoon cycle. So how to model that? Or some of you might have come across studies which tells how the carbon cycle is getting affected due to reduction or greening of forest cover. All these things are kind of really complex problems which, as scientists, we are all trying to address in different phases. So what are the common thing between all these problems? If you look at the questions that I posed in the previous slide, almost all the questions will be having some critical data as its prime requisite. That is, the first question, what is the impact on water resources due to change in land use, land cover? So definitely it shows we need land use, land cover data, how land use, land cover was there in the past, at present, and how it will change in future. And to track hurricanes, we need to know what is the current location of hurricane, what is the size of its eye, at what pressure it is, what is the pressure in the center of the hurricane, all those like meteorological factors people will be needing it. Third question I asked, what is the effect of change in cropland or change in irrigation patterns in monsoon cycle? For that, we need to know what is the extent of cropland, what type of crops being cultivated there, and how much of cropland is being irrigated, and so on. And similarly, for a question related to forest cover, whether forest cover is really changing, if it is changing, if it is decreasing or increasing, how the vegetation property is changing, whether the forest is greening or browning, what is the carbon stock in the forest. All these kind of data sets will be needed to answer the questions that I posed in the previous slide. So essentially, without these critical data elements, we will not be in a position to do our analysis and reach a scientifically valid conclusion. You cannot say like, yeah, due to forest greening, this is happening, or whether forest is really greening or not. That itself is a major scientific question. Some people are telling it is greening, some people are telling it is browning. So the availability of critical data elements at the right time is really crucial to answer such complex questions related to Earth system sciences as a whole. So the answer to most of our data needs, at least for the problems that I have mentioned in the previous slides, is remote sensing. So what exactly is remote sensing? You people should be knowing this, at least the definition. So remote sensing is nothing but obtaining information about something, whether it's an object or a phenomenon or whatever, obtaining some information through data collected by non-contact ways. That is, say like you want to understand whether there is kind of like a fire or not in a forest region. So what we will do, without going there, we will take satellite images and see whether there is a fire burning there. So the satellite acquires images from a good distance from the actual area of our interest. So the data that we collect is not in a physical contact mode, but using a remote mode. That is, we are collecting the data remotely, and we analyze the data further to get more information about the object of our interest or phenomenon of our interest. So remote sensing is essentially a data collection method or technology where the data is collected through non-contact means, and using the data, by processing it, by subjecting it to various kinds of analysis, we can get useful information about different phenomena that are occurring in the Earth's surface as a whole. Just to give a brief evolution of remote sensing, how this started and how it progressed, just to give a feel for where remote sensing stands right now as a technology. Okay, so the basic interest to see the Earth from the sky was there for a very long time. Even like there is a quote by Socrates, I guess, if I remember correct, that in order to appreciate the Earth better, you should be seeing the Earth from above the atmosphere. That was like one of the quotes made by Socrates, I guess. So people are always wondering, or in fact wanting to observe Earth's surface from a distance from a distance from sky or space, whatever may be. So it is always there. People always wanted to fly and observe the Earth from a bird's eye view. And initially, it started when people started to fix cameras in balloons, or even to kites, large kites, or even under the legs of pigeons. People used to tie small photographic films there, or people used to like sit in balloon carrying their camera in hand, go to the sky and take pictures. All these things were happening in the 17th, 18th century. In fact, like one of the first photographs taken from balloon by a person, Gaspard Felix Tournacon. He is like known as Nadar. In short, he is like the first one to take pictures from balloons, which really went on famous, and people started appreciating this as a taking pictures from the sky and using it as a technology itself. Initially, the photos that were taken from these balloons were used for qualitative interpretation purposes. Interpretation means like if you observe a picture or if you observe a photograph, you will see like, okay, there is a lake, there is a house, there is a go down, there's a swimming pool. All these things we observe and mark what is what. That is commonly we call it as photo interpretation. That was the initial use of remote sensing. And later during World War II, people used to collect photographs over strategic enemy locations and use it for their warfare purposes. After this only, people understood the real application of remote sensing, or the real potential of application, real potential of remote sensing, and then people started sending satellites up to the space. And even after like 1 or 1.5 decades after sending the first satellite to space, remote sensing was mostly confined to qualitative. Qualitative means, okay, take an image and map what is what. People will be sitting on a light table, manually digitizing, okay, this is a lake, this is like a geological structure, like that. Everything will be mapped on a qualitative basis. But still, it was like really useful at that particular time, which saved a lot of manual field work to the people. From 1980 onwards, scientists saw the potential use of remote sensing for quantitative purposes. Quantitative purposes in the sense like what is the real use in a a real numerical sense, rather than just seeing and telling there is a water body, there is a lake or something. What if I try to sense what is the depth of the lake, what is the height of the tree, how much is the vegetation growing in that particular tree? All this kind of quantitative things started to come from the 1980s onwards. And from 1990s onwards, there was like a huge development on the new detectors, which expanded the portions where we can see. And now at present, most of the remote sensing studies are oriented towards quantitative observation. So now the entire paradigm has shifted from being qualitative to quantitative. So what exactly quantitative I mean? Say what is the loss of carbon or gain of carbon in a particular forest stand. That's a quantitative study. We do that. What is the potential yield we can expect from a particular croplands or within a croplands located in a particular district? It's a quantitative study. We are able to doing it. What is the surface temperature being experienced by particular city? We use it for various meteorological applications. That's a quantitative observations. So all these kind of quantitative observations are now the principal aim of remote sensing based studies. Okay, just to again give a brief overview of like where we experience remote sensing. We do remote sensing actually in nature. The process of our vision itself is a remote sensing purpose, because whatever objects we see, we don't go and touch the object to feel it. We can see the object through our eyes from a certain distance, right? So that is a remote sensing that we do in nature. Or similarly, like we can hear sounds of objects that are far apart from us. Like if a train is moving on at a farther distance, we can hear the sound. Or if the baby is crying in the next room, we hear the crying noise and go to the room to pat the baby. All these things are examples of remote sensing that we normally do in nature. Actually, this kind of natural experiences only are currently being translated from outer space, so that we can apply the same principles to see the earth from a completely different perspective. Okay, so what exactly a remote sensing system comprises of? What exactly we do in remote sensing? You should be knowing this too, but just as I said, to brush up the fundamentals, I'm telling this. So we have like a source of energy which gives us energy to do the sensing. Like since we are not going and physically touching any object, we need some medium which carries the signal, right? Say for example, through our vision, we are sensing light, and the light carries the signal of all the objects in front of us. Whether there's a laptop in front of me, there are a few books beside me, all the information about those objects are carried to my eyes by light. So light is acting as a medium, and I need some source of light. Without light source, I cannot see those objects. If it is pitch dark, if my room is pitch dark, I cannot see the objects. So the light source is naturally it is sun. Now there is like a light that is glowing inside room. So some source of energy which will give us the energy where we do the sensing. Normally for our remote sensing purposes, we take sun as our primary source. It sends some energy towards the ground. That energy will come towards the object of interest, fall on it, will be reflected back and going to outer space. So this energy now, after being reflected back from the Earth's surface, now this signal will be carrying the signals about the Earth's surface. So this particular path B, while it is going towards the space, is really important as it carries the useful information about the Earth's surface. Then we place a satellite along with a sensor in space to collect this particular signal and store it in form of an image. Most likely, most of the remote sensing outputs come in form of image. There are other non-imaging sensors too, but we won't touch it. So let us assume it forms an image very similar to a photograph we take. So very similar to a camera, we take a photograph. Same thing happens here. The sensor takes a picture of what is there on the Earth's surface. Then that particular image will be transferred to the ground station through some different means, and we will be able to collect that image, work with it, or analyze the image using various analysis techniques, and finally we use that particular image for our applications. So this is the actual life cycle of a remote sensing system, starting from origin of energy to interaction of the energy with object, collection of energy by the sensor, and forming an image, getting the image of the Earth system, finally processing the image and using it for various applications. Okay, what are all the basic advantages of remote sensing? First thing, it's a non-contact and non-intrusive procedure. As I said, we are not in physical contact with the object of our interest, and hence we are not disturbing the object of our interest. We are not going and touching it or not disturbing it, and it's non-intrusive. Being non-intrusive, it also provides access, remote access to wherever we want to observe. Say there is a forest fire happening, I cannot go inside the burning forest to collect data. I have to do it from space. If there's like a hurricane happening, I cannot go to the eye of the hurricane to collect meteorological information. I have to do it remotely. So this non-contact may provides me a remote access. Then comes a repeating nature, like this, same point on the Earth's surface will be imaged again and again, which can be used for temporal analysis over a period of time. And then remote sensing provides a synoptic view. Synoptic view in the sense like a large area will be covered in a single snapshot. That is possible. It provides global or regional coverage. Entire globe can be covered in a certain period, or some same region can be viewed again and again. And the most important thing is remote sensing helps us to see and obtain information in portions of energy where humans cannot see. That is, our eyes are tuned to see only like white light, basically like whatever the visible light that comes from the sun or which is produced by the light sources we have. But still, the entire energy spectrum is really huge. The radiation spectrum is extremely huge, and visible light forms only a tiny part of it. So our eyes can see only like a very small fraction of the world in its truest form. There are like other forms of energy in which the objects will manifest themselves in a completely different way. So through using remote sensing, by developing new sensors, we will be able to see the objects or phenomenon in how they behave in different portions of the energy spectrum, other than the visible spectrum that we see. So this is one of the major advantage of remote sensing, right? Okay, I just said like we are able to do synoptic coverage, we are able to do a global or regional coverage and all. I just wanted to give a quick glimpse of how these things happen basically. So in the next 2 or 3 slides, I have like a series of videos which shows you how the Earth is being observed from satellites in different orbits. So the first video that I'm going to play will tell you how the seasonal changes occur, how sunlight falling on the Earth at different seasons. It is observed from a satellite in a geostationary orbit. So geostationary orbit means the satellite is located at a distance of 36,000 kilometers away from the Earth, and the satellite, that particular satellite, will be seeing the same point of the Earth's surface throughout its life period. So the same point will be visible, and that particular example I will play in this video. So yes, so this particular video is actually showing us how the Earth's surface is kind of rotating. So sun is oriented in this particular direction. Sunlight is coming from here. So what I want you to observe is, see the time scale here. So the time scale is like for one whole year, starting from to the 10/9/19 to 11/9/19. So it's one full year, 2010 to 2011. And this is like, even if you run for the entire image, I'm just running the image again, you can see the African continent in a constant way. So this particular satellite sensor observes the same point of the globe throughout the life cycle. So what it means, one portion of the Earth's surface, entire Earth's surface, will be seen constantly. Maybe every 15 minutes once or every 30 minutes once, you will be getting the data. So this is one example of constant view of the same region, but it also provides like a large synoptic view. The entire hemisphere is being seen from the sky. Okay, so this is an example for a regional coverage. So we saw only like one particular region, but what if you want to see the entire globe? There is again another orbit called the polar orbit, from where we will be able to see entire Earth. So this is an example for it. Like the satellite now will be moving around the Earth almost in a perpendicular direction to Earth's motion, and Earth will be moving under it again in perpendicular direction to satellite motion. So essentially what happens is, Earth is moving from west to east, satellite will be moving from north to south regularly in a fixed orbit. So different portions of the Earth will be covered as Earth and satellite moves together. So this is one example of providing a global coverage. Okay, so in this slide and the previous slide, I mentioned few words: spatial resolution, temporal resolution, and so on. So what exactly is spatial resolution and temporal resolution? A sensor in a satellite, you can imagine it very similar to a camera that you have. Even your camera will have tiny sensors within it, like many detector elements will be there. Whatever picture you take, the energy from the outside world will come into the camera, will be get recorded inside the detector element. Same thing applies to satellite. Satellite has many small detectors. It is carrying the detector at certain height from the ground. So what is the area covered by one detector element on the ground? Say this is like one single detector element in the satellite. What is the ground area coverage? Some satellites may have a coverage of just 1 meter. Like the coverage will be very small area. Some satellites will be having a coverage of 5 kilometers. That is, one single detector will be able to cover 5 kilometer by 5 kilometer in ground area. Whereas for some satellites, a single detector will cover only 1 meter by 1 meter area. So this is what we call the spatial resolution, or rough terms. It's not an accurate definition. Just for our purpose of discussion, I am simplifying it. Okay. So this is what is known as spatial resolution. So what is the spatial resolution we need for our climate studies or for our studies related to water resources? It depends on the application. Maybe that's the point I mentioned here. Before that, I'll just cover this temporal resolution. So spatial resolution we have seen, and temporal resolution. Temporal resolution is how frequently we get the data over the same region, whether it is 16 days one image, or one image every day, one image every 30 minutes. Like in the first example I have shown you, like the Earth season, how the Earth season changed. That geostationary satellite can take a picture of Earth, like one image every 15 minutes. So we will be getting almost like 4 images per hour, and I think 96 images per day. On the other hand, polar orbiting satellites, that is the previous slide, like this slide I showed an example, those satellites can get maximum like one image per day, or one image every 15 days, one image every 16 days, like that. So that is temporal resolution. As I said before, there are no predefined values of this spatial and temporal resolution for different applications. As researchers, we have to choose what is the spatial and temporal resolution needed for our own applications. Whether I want to study how urban area is expanding, I may be needing a spatial resolution of say 2 to 5 meters or even finer, but temporal resolution of say 1 year or 2 years, that's fine enough for me, because urban growth will be happening in a minimum of annual scale. Whereas if I want to study hurricanes, I'm a meteorologist, then I'll be requiring data once every 30 minutes or even 15 minutes, but I will be needing data over a very large region at a much coarser resolution. Say 1 pixel covering just 5 kilometer by 5 kilometer will be good enough, but I'll be needing data every 15 minutes once. So the requirement of spatial and temporal resolution depends on applications in which we work on. It's not, there is no hard and fast rule to tell this is the best spatial resolution and this is the best temporal resolution. We have to be judiciously choosing what resolution we need for our own applications. I just showed you the most popular two orbits of Earth, or orbits that satellites, revolve upon. They are like the geostationary orbit and the polar orbit. But there is another orbit which is like not like an orbit, but it's like a fixed point on the Earth's surface, which we call the L1 Lagrange point. There is a satellite called Discovered and a camera called EPIC, 1.5 million kilometers away from Earth's surface, taking pictures of Earth for various climate-related applications, especially. And I just wanted to show a glimpse of how Earth looks from that particular sensor. So just enjoy this particular video. Nothing like scientific. So here in this particular video, say moon is crossing in front of Earth's surface. That has been imaged by that particular sensor. 3 hurricanes simultaneously occurring over the Pacific Ocean, which is one of the rare occurrences imaged by that particular sensor. The North Pole, which is like normally our satellites will miss to see. Polar orbiting satellites will not be able to cover the North Pole and South Pole regularly because they are not actually polar. We call it as near polar. So this particular sensor captured the North Pole and South Pole. Smoke, like here in this particular region, we have smoke. Moon shadow due to a lunar eclipse that is passing. So the black portion is a moon shadow. Another moon crossing. So these are some of the examples of observing the Earth from a completely different orbit. So seeing the Earth from our own eyes perspective and seeing the Earth from a completely different point will show us like a really new things about the Earth's surface, how the Earth looks, how the Earth behaves. All these things we can get. Okay. So how are we sensing remotely basically? So we are sensing remotely, as said before, by sensing some energy signals. Like our eyes sense light. There are like other portions of energy medium. So what exactly is it? For remote sensing purposes, we use what is known as an electromagnetic radiation. So what exactly electromagnetic radiation is? Electromagnetic radiation is nothing but a way in which energy propagates itself. Like it's a movement of energy from one point to another point through radiation. Means through radiation, energy transfers it from one point to other point. So EMR is how energy propagates itself. So that's it, nothing much. Mostly we think EMR as a wave, and we have studied in like high school physics that when wave travels, each wave has associated wavelength with it, associated frequency with it, and also electromagnetic radiation travels with the speed of light in vacuum. Okay, so wavelength and frequency will tell the characters of the wave. Longer the wavelength means like each wave to complete one cycle, it will travel a really long distance. Say here if I label it as wave A and wave B, wave A has longer wavelength than wave B. Similarly, wave A has shorter frequency than wave B here. So frequency is the number of cycles in a unit time. Wavelength is the distance covered by a wave to complete one full cycle. That's it. So starting from this point, going to a peak, coming to a trough, and then again coming to the zero. So this is like one full cycle. So what distance it covers? So essentially, if the frequency is more, energy content of the wave is more. This also we would have studied in our physical classes, physical science classes. So what exactly is electromagnetic spectrum? Electromagnetic spectrum is nothing but whenever energy is produced by an object, like even us as humans or whatever object surrounding us, everything is producing some form of energy due to its own temperature. Some energy is coming out of it continuously in form of electromagnetic spectrum, and that particular energy will not have a unique wavelength. It will have a mix of different wavelengths having different energy levels. Say like whatever energy we are emitting as human beings, we will be emitting waves, electromagnetic waves or electromagnetic radiation, maybe starting from infrared portion uh, and thermal infrared portion, even some portion in microwave. If you look at sun, a really hot object, it is emitting energy primarily in the visible portion, ultraviolet portion, infrared, and so on. So based on object's energy level or object's temperature, each and every object will produce a continuum of energy. And if we combine all this continuum and put it on one continuous scale, we get what is known as an electromagnetic spectrum. So electromagnetic spectrum essentially spans between an extremely high frequency wavelength like the gamma rays produced in nuclear reactors, or like what to say, hot ball of fire like sun. Gamma rays are produced there due to its very high temperature and nuclear fusion reactions happening. So they are like really high powerful waves which can what to say, mutilate any objects lying in front of it. From that particular high frequency low wavelength spectrum to a completely low frequency high wavelength spectrum of radio waves, which we use it for our communication purposes. So electromagnetic spectrum spans a very huge what to say, dimension of wavelength. You can just look at the numbers here, starting from 10 power minus 12 meters to 10 power 3 meters. So it's like a very large difference in the spectrum. So EMR is nothing but a combination of all the different wavelengths in which energy propagates itself. That's it. So that is EMR spectrum. And as I said before, our eyes can see only in the visible portion of EMR. That is the white light, which is like extremely tiny when you compare this entire spectrum. Remote sensing help us to see in all the different portions. We can do remote sensing infrared. We can do remote sensing of Earth in microwave. We can do remote sensing of Earth within infrared. There are like a lot of small portions which we can do. So remote sensing help us to see how objects will look when we see them through the other portion of the spectrum, like the different portion of spectrum other than visible. Okay, so that is the major advantage of remote sensing, and this is what known as electromagnetic spectrum, like this span of energy. So just for your information purpose, I have listed here broad classification of electromagnetic spectrum. Like as the spectrum is really huge, for our own convenience, what we did is we have divided the spectrum into small wavelength bands, like from a minimum value to a maximum value, like a small range we have given, and for each range we have allotted a name. Like say for example, what our eyes can see, 0.4 to 0.7 micrometers. The unit is micrometers. That is 10 power minus 6 meters. This we call it as visible portion of electromagnetic spectrum. Similarly, we have what is known as a near infrared portion. We have what is known as a long wave infrared portion. All these things. It is a name that we have framed for our own convenience. We have divided the huge spectrum into small ranges or small blocks and given a name for each block. So almost all the objects on the Earth's surface will behave completely differently when we look through each and every portion of the electromagnetic spectrum. Okay, what are the prime sources of electromagnetic radiation for our own remote sensing purposes? As I said before, sun is the primary source. Like sun generates different portions of EMR. It transmits the energy towards the Earth's surface. The energy interacts with the Earth, goes back to the space. Sun is one mode. And as I said again before, all the objects on the Earth's surface will be continuously emitting EMR due to its own temperature. So even we ourselves are a source of EMR. Like maybe some of you might have experienced the temperature testing through like that handheld thermometer, like a radiometer. We call it as a radiometer or a small handheld thermometer. People will be pointing that thermometer towards our forehead. They will be saying, okay, you are fine, you can go. Like in airports they do, in railway stations they do. That's a remote data collection, and that temperature collection is possible because our bodies will emit radiation, and that handheld thermometer collects that radiation, process it, and tells how much temperature, how much temperature our body has. It's a remote way of data collection. That is because our body is also a good emitter. That is like, so each and every object in the world on this Earth surface itself is a source of EMR. Or on the other hand, the sensor itself can produce its own EMR. There are like sensors called radar or lidars which can send its own signal and it will be like falling on the object, coming back. They will record that particular energy and try to form images out of it. So remote sensing can be carried either in active manner or passive manner. So active manner means the sensor itself will produce some energy, send it towards the object, collect it back and use it to form an image. Like the best example is a camera attached with a flash. The flash is an active source. Flash gives white light that travels and illuminates the object of interest. Or passive manner means whatever the object is reflecting from sunlight, we are collecting it. So a camera without flash is a passive manner. And the handheld thermometer they use for this corona temperature testing, it's a passive data collection. So our earth itself is a primary source or sun. So what we are actually doing, we are either collecting the energy that is reflected from the earth's surface, that is earth's surface, sun is there, some energy is coming in, it is reflected to space and we are collecting that particular energy. So this is reflected energy. Or if you are able to sense in a portion where earth is releasing energy, we will be directly sensing it even without the need for sun. So this we call emitted energy. So we can sense either reflected energy or emitted energy for our remote sensing purposes. So this is what is given in the slide. What exactly are we sensing in passive mode? We are sensing either the reflectance of an object, how much an object reflects, or we are sensing how much an object is emitting. So this is just to give an example of like how different objects will reflect differently. Maybe like I'll not go into details, but just to know different objects will reflect differently. Everything is not the same thing. That's the only thing I wanted to convey from the slide. Okay, from this reflectance, what we are actually doing and how we are able to classify what is what on the Earth's surface. Like as I said before, the earliest examples of or the earliest use of remote sensing was to qualitatively map the features on the Earth's surface. Like this is a cropland, this is an urban area. People use it for mapping it manually. How they are able to do it? They are able to do because of a concept known as spectral signature or spectral reflectance curve. What exactly is a spectral reflectance curve? There are like remote sensing, we can sense in a broad wavelength. Here you can see like we are sensing from 400 nanometers to 2400 nanometers. We will be seeing the energy coming out of the object. What fraction of the energy is reflected by the object is what is known as reflectance in the y-axis. So at this particular portion of electromagnetic energy, like 800 nanometers, that particular object is reflecting almost half of the energy falling over it. Whereas if you look here, say like the 500 nanometer portion, the object is reflecting only 10% of the energy falling over it. So each object will behave differently when seen through different portion of EMR. Like if an object appears bright, like high reflectance means it will appear bright, okay, basically. So if an object appears bright in one wavelength, it may appear dull in another wavelength, like dark in another wavelength. So each object has a characteristic curve, how the reflectance changes with change in wavelength. This is what is known as spectral reflectance curve. And almost all objects on the Earth's surface has a nearly unique, I will say not perfectly unique, but nearly unique signature. Like vegetation has a unique signature, water body has a unique signature, urban areas has a unique signature. Like the curve will have like a typical pattern. Like here I am showing you in this particular slide. There are like multiple objects. Water is there. This small dotted line on the bottom is curve for water. This dark black line is for the grass, and this line is for sandy clay soil. Yeah, and this is for sand, and so on. So different materials on the Earth's surface has a completely different reflection property or a reflection curve. Its reflection will change. Using this as a clue, like what we do normally is we collect such reflectance data from ground measurements as samples. Over small areas, we will collect samples and keep it in lab. Satellites will be continuously collecting such signatures from space. We'll be, to put it in a simple sense, we'll be trying to match, okay, this is a satellite-based spectrum, this is a field-based spectrum, can we match it? If we match, what object it represents? Is it a vegetation? Is it representing a water body? Is it representing like a sand? We can get it. So this is the basic way through which we classify different objects using remote sensing. So the concept that you have to remember is what is known as spectral reflectance curve. But a word of caution, a same object may look completely different when observed from different angles or different environmental conditions. So there are like good examples. They are like same field. On the left you have like a same vegetation, like same crop field, take photographs being taken from different locations. Here also same thing, same forest stand, photograph taken from different angles. They look entirely different. So this is what will happen, because most of the objects are they will reflect radiation, but in a completely different way. Here, not only with respect to vegetation, but also with respect to soil, same land, with photograph being taken in two different angles, one from here and one from the other side. So the image on the other is image taken from the other side. They look entirely different, because an object may look completely different if photograph is taken again. But in remote sensing, we are able to come over all these obstacles. There are like a lot more obstacles there. Not, I'm just telling you the most fundamental things. There are a lot more obstacles, but still we are able to overcome them and use it for our applications. Fine. Till now, I have been talking only about fundamentals of remote sensing. Now I will quickly share, like we are almost 45 minutes into the talk. I just wanted to share how remote sensing is useful to climate or earth system studies. The topic itself is remote sensing for earth system studies. How it is useful, that's what we are going to see here. So the figure right now I'm presenting in the slide is, which is a schematic of how an earth system model will look. Earth system models are nothing but a complex model which tries to simulate different components on the globe, whether it is a water cycle, carbon cycle, meteorology, biophysics, or what to say, or biomes or ocean processes, whatever. And earth system models in general model all these individual components of the earth system as a whole, and try to study the feedback between them also. Like normally if you take a terrestrial biosphere model, it will study only the biosphere part, how vegetation is behaving for change in carbon concentration. Or if you take a hydrological model, it will study only the hydrological part. If you take only an ocean circulation model, it will tell you how ocean water is moving due to varying temperature and varying salinity and all. But an earth system model, in addition to modeling these individual components of earth system, it also tries to study them with respect to their feedback. What is the feedback between ocean to land? What is the feedback between land to the atmosphere? What is the feedback between ocean and atmosphere? How vegetation is influencing terrestrial climate processes. All this feedback cycle also will be included in earth system model. So earth system model is kind of like a really complex representation of the earth system, different components of the earth system, along with the proper feedbacks. Okay. If you look at this, it has lot of variables involved. The entire slide is filled with variables, starting from chemistry of atmosphere, like CO2 concentration, CH4 concentration, what is the amount of like vegetation present, whether it is deforestation going on, afforestation going on, what is the, whether snow is present, how much carbon is going out of soil or crop, what is the energy going in, like what is the latent heat flux going in from the land to the atmosphere, what is the soil moisture here, or if you take the ocean, what is the chlorophyll content of ocean, what is the temperature of ocean waters, that is sea surface temperatures. Here are like hundreds of variables will be needed by such complex earth system models, and only by providing the model with good quality data, we will be able to do good quality modeling study and arrive at useful results. So remote sensing provides data in multiple, small cycles of this earth system. If you take ocean, remote sensing provides you ocean surface temperature, we call sea surface temperature, SST. It provides sea surface temperature. What is the chlorophyll content of oceans? Like we study the phytoplanktons, we study ocean water salinity, all these things affects ocean circulation. Or if you take the atmospheric system, we study the meteorological phenomenon, temperature, pressure, rainfall, all those things we study from remote sensing satellites. Or if you take land cover, we study what areas covered by vegetation, how well vegetation is growing, like we study the vegetation vigor, we study vegetation water content, we study how much water is being transferred from land to atmosphere as evapotranspiration. We are measuring how much water is there in the soil as soil moisture. There are like countless number of variables that are being observed by remote sensing satellites, either directly observed or from one observation and using some physics we get to another variable. So this is what I'm going to show you in the coming slides. These are some of the examples that I have like taken from commonly available satellite sources, and the last slide ET is like our own group's work. So this particular slide shows how green the earth is. Here this is a variable called NDVI, normalized difference vegetation index. So this will generally vary from over land, it will vary from 0 to 1. So 0 means like completely dry bare surface, like over like these deserts. Here there is a desert, over here there's a desert and so on. Whereas these portions, Amazon forest, here there's a forest, rainforest in Africa, the small Western Ghats, which is like densely forested. So they are having a value close to 1. So essentially, the green patches tells us vegetation is doing good there, and the yellow patches tells there's no vegetation, it's a dry bare surface. So this particular image tells us where vegetation is present and how well the vegetation is growing. This is an important variable into global climate models, terrestrial biosphere models, or even like a carbon simulation, like carbon cycle models, and many things. Without vegetation properties, we will not be able to study most of the variables, be it hydrology, be it climate, be it meteorology. We need vegetation information. This is land surface temperature, how hot or cold land feels. This is not air temperature, what we see in newspapers. This is how hot or cold land feels. So again, this is one of the primary variable for meteorological purposes, for studying urban heat island studies, for doing like modeling evapotranspiration, for mapping soil moisture, etc., etc. So here like the blue patches are cold patches, and yellow patches are like hot patches. If you compare the figure, the previous figure, you can see like this central portion of Africa, which is like forested region, it has kind of like a lower temperature. If you look at this desert here, no vegetation, high temperature. So there is like a kind of like a, not always, but there is like an inverse relationship between presence of vegetation and land surface temperature. It's not true always. There are other factors that influences, but more or less it holds at least in tropical regions. This is one example related to meteorology, that is aerosol optical dip. Higher the aerosol optical dip means like higher is the aerosol content in the atmosphere, which may be harmful for us. Like it's a kind of like a health hazard. Higher aerosol presence may, what to say, stop sunlight from coming, it may produce haze, it may cause breathing difficulties, and so on. So this is one of the variable needed in meteorological studies, health monitoring studies, and so on. This is one related to ocean application. What is the chlorophyll content of ocean? So the chlorophyll content or the phytoplankton content in ocean determines how well the ocean water is mixing, how carbon is assimilated into ocean. These phytoplanktons are good source of carbon sinks. They take in carbon, sink to the bottom of ocean when they die. They are extremely good source of carbon sinks. So modeling the phytoplanktons or chlorophyll in ocean will tell us whether the ocean is acting as a carbon sink or not itself. Very important variable in carbon studies, ocean circulation studies, and so on. And this is like a map of evapotranspiration produced by our own research group here. So this will tell us how much water is being evaporated from land surface at a monthly scale at a pan-India level. So this will tell us like how much water is going to the atmosphere, which portions of the country is doing it, and at what time it is doing. Okay. So maybe this will take us to the end of this presentation. If you are really interested in knowing more about the role of remote sensing in different applications related to Earth system as a whole, I will suggest you these really excellent papers. One of the papers by Sheffield and others, which will tell us satellite remote sensing for water resource management. they will give like a whole broad overview of like where remote sensing can be used for different applications. This is the future of Earth application, Earth observation hydrology. Again, another really good paper which tell how Earth observation will look in the near future. And if you are really interested to study the Earth system as a whole, then you can go ahead and see these two papers, one by Balsamo and others, and one by Kaminsky and others. So with this, we come to the end of the slide. And thank you for your patient listening. And I'm open for questions now.
So can you hear me?
Yeah, I can hear you, Shiva.
Okay, so we'll start displaying the questions. Please
Yeah,
hold
sure.
on for a second. Yeah.
Yes. Okay, first question is, what is the difference between weather model, physical model, or Earth system model? It's actually like weather model and Earth system model I can compare. Weather model is kind of like a meteorological model. It models different processes of meteorological elements, rainfall, temperature, and so on. Earth system model, as I said, it's like it covers like entire domain of Earth system itself, like different cycles of Earth system. Like meteorology or weather model is just one part of Earth system model, how weather evolves. Similarly, there are like other components of the Earth surface like hydrology, cryosphere, biosphere. There are like other different spheres of Earth surface. So Earth system models try to simulate all of these things in a combined fashion along with the feedbacks between them. So weather model is like a standalone model related to meteorology, whereas Earth system model is like a combined one which models different processes of globe. This is one thing. And physical model is this is just to deal with how you are getting your simulations done. Whether are you using physically based equations, or you solving those equations mathematically, then you can call the model as a physical model. There are like other empirical models which will tell like, okay, if this is the input, this is the output. We call it as data models, database models, or empirical models, or black box models. So physical model deals with how we are doing modeling, whereas weather model and Earth system model are to deal with what processes we are modeling. They are like different classification of models. Yeah. What decides resolution potential of a satellite? 1 meter, 30 meter, etc. Okay, the resolution of a satellite is fixed by various factors. First thing is, whenever a satellite is being planned, even in planning stage, they will decide for which application they are going to use. Based on that only, they will fix what resolution to send the satellite with. So the resolution of the satellite depends upon at which orbital height it is located, what is the power of its optics, what is the capacity of its detector elements, whether the optics is really good or not, how much time it takes to observe the Earth's surface. Some satellite sensors observe the Earth's surface in extremely quick time, like the time will be in the order of microseconds, 10 microseconds, 20 microseconds, 80 microseconds, and so on. How much time it takes to observe the Earth's surface, on all these things it matters. So deciding the resolution potential is like many different factors are there. But as I said before, whenever a satellite mission is being planned, they will see what are the potential applications of this satellite mission. Each satellite mission has its own set of applications. All satellites cannot be used for all the applications. So they will say, okay, this is a satellite, this is the application I'm going to use. So this is the optimal resolution for that particular application. Say, for example, as I said before, if you want to study urban area, like how urban areas changing, the best resolution for you may be 2 meters or 5 meters and so on. So such satellites will aim for a very fine spatial resolution. Whereas satellites that are sent to space for meteorology, they will design it to have a spatial resolution of like 4 meters or 4 kilometers, 5 kilometers, and so on. It depends on application. and it will be decided even before the satellite is like finalized. Yeah, next question, please. Which satellite is better to use for differentiating between forest and agriculture land? Okay, forest and agriculture, both according to satellite, it is like vegetation. Okay, so which satellite you use, if the cropland also has vegetation like crops, and if forest also has good vegetation, they will appear almost similarly. But one thing, whatever satellite you use, what we can do is to identify a cropland or a forest land, we can use multi-temporal image analysis. Multi-temporal means a cropland will have like a definite phenological stages or seasonal cycle. We will be definitely knowing what is the season in which the farmers plant the seeds, where we can expect a small plant growth, where it will reach its maximum, then when it will senesce, when we can like harvest the plant. So croplands will show like a typical phenological stages of crop growth, whereas forest, deciduous forest may have a phenological cycle, but if it is evergreen, it may appear always green and so on. So that is one thing, like you can observe multi-temporal images, or you can choose like data at different resolutions. Normally different resolutions means like now there are like plenty of satellites available, Landsat 8 is available, MODIS is available. You can like take images at different resolutions, compare them. Croplands normally will be at a smaller scale, especially if you are studying over India. Croplands will be much smaller in size, so they will be clearly visible in high spatial resolution satellite like Sentinel-2. You will be able to see like 5 meter by 5 meter, 10 meter by 10 meter. MODIS can be used for forest studies. In MODIS, individual croplands cannot be seen, at least in Indian conditions, but you can see like huge swath of forest. So I will not suggest any one satellite for mapping vegetation, for differentiating forest and agriculture land. Almost all satellites will see them as vegetation, but the way you process the data, by using like a combination of high spatial resolution, low spatial resolution imagery, and by using multi-temporal image analysis, you will be able to easily distinguish between a cropland and a forest land. Which satellite should I prefer to study district level LULC, Sentinel-2 or Landsat? Again, it's up to you. District level LULC, both will be good enough, or even like Sentinel-2 maybe sometimes somewhat higher data load also because of its high spatial resolution. What resolution you are working on, you first decide whether you need data at 30 meters, whether you need data at 10 meters, and whether you need data at 100 meters or 500 meters and so on. First thing you should decide. Second thing is, what is the time frame of LULC analysis you are doing? Are you doing for like last 30-40 years? Then definitely Landsat is your choice, because Landsat has like a long time period of record starting from 1970s itself. So you can do like 50 years of LULC analysis. If you want to study land cover only at present, you can go for Sentinel. But as I said, you have to decide upon at what resolution you need. If you're happy with 100 meter resolution or so, better go for Landsat with its slightly closer resolution and also its longer time frame. So again, it is like up to what we choose. But if your resolution demand is like slightly lower, 100 meter or 30 meter or even closer, better to go for Landsat because of its smaller data size for downloading and as well as a longer time period of record. Sentinel-2 is really good, but you may have to use or download a huge amount of data because of the image size. It has a lot of bands, fine spatial resolution, so the image size will be much larger. If you are able to filter it out and download only certain bands, you are fine. India too has meteorological satellites. Why are products from them not being commonly used? It's an excellent question. The reason for Indian meteorological satellites being not used frequently is they are not widely known among the scientific community, because like ISRO had like somewhat the data was like kept in like a cold storage. That is one thing. And till recently, most of the data were available for purchase on a price, whereas US like Landsat series and MODIS became absolutely free. So there was like a first thing, people are not aware. Second thing, we have to pay some amount of money to get the data. Till previously, now most of the data are free. Till few years before, we have to pay some money to get lot of data, whereas MODIS and Landsat data were free. And what to say, the data ordering process, like ISRO developed their data processing system on completely online again very recent. Like while I was doing my UG, most of the ISRO based data sets were not available. I have to like write to NRSC and get it. But right now we can like sit from the comfort of our home and download it. Whereas like even before like 15-20 years, NASA had its own portal where people can search data and download from the comfort of their homes and offices. So these are all the major differences why Indian satellites haven't received much attention. Major thing is no visibility for them. But right now, our group, my research group in IIT Bombay, we are having like a lot of projects with ISRO where our main aim is to use Indian satellite data to model different hydrological processes. Like in the slide I showed you evapotranspiration map. Now currently there is a project under me in which I am trying to use data from INSAT 3D, an Indian meteorological satellite, and use it for modeling evapotranspiration. Similarly, there's a mission called OceanSat 3, which is like coming up. The data will be coming up. So we are also planning to use it and use it for different hydrological applications. So now the visibility is increasing. Soon we will be seeing like a lot of Indian satellites also being used for various applications. Does RS provide information on CO2 release from soil? Yes, RS provides information on CO2 release as a whole, but it is difficult to say whether it is from soil or from vegetation or from different sources because satellites see everything together in one single snapshot. So it will be difficult for us to really tell whether it is from soil or it is from vegetation, but you can take the whole data and use it in maybe carbon cycle modeling studies to constrain the models and say like, okay, this fraction is from soil, this fraction is from vegetation, and so on. So RS itself cannot provide what is from soil, but it can provide CO2 as a whole for the entire environment, composing of animals, plants, soil, and everything together. Yeah. With the help of satellite, can we be able to identify the type of crop cultivation done? So I understand this question deals with identification of crop, like which crop is there. Yes, it is possible. There are like studies to tell which particular crop is being cultivated in a given region. People are really doing it, and it has like a very wide applications, especially in the agricultural insurance sector, for agricultural planners, for food safety measures, and all those things. It is possible. People are doing it. Even like one of my PhD student is working on like crop classification, we call. So crop classification from using like different machine learning techniques and remote sensing data. It is possible, and many people are doing it. Yes.
So whatever questions we received in the Q&A sheet we have shown you, shall we wait for 2-3 more minutes? Maybe the viewers have more questions. We can wait for 2-3 minutes.
Fine, no.
As we have time.
Yeah. Okay, question has come. Can we get data for doing studies on land and water use diversification in coastal areas for a time series? Actually, I'm not really able to understand what Ashok is asking me. But if I understand it correctly, like it is related to like classifying or demarcating land and along the coastal area, demarcating land and water. It can be, or how much is the coastal area is changing. Yes, like almost all satellite data you can use, like Sentinel, Landsat, and everything. There is satellite, and Sentinel has like a lot of times in a large time series. Landsat has a really large time series. Yes, there are plenty of satellites. You can always use it for coastal applications. And Oceansat 2, Oceansat 3 of like India, they are like especially they have specific bands to study like ocean and coastal related processes. You can use Oceansat data also if you want to really study like how coastal areas are changing. That's a good bet. There are satellites.
So we have 2 more questions. Please hold on and we'll just display it for you.
Yes. Can RS be used for underwater assessment, bathymetry assessment? Yes, it is being used. There are like specific wavelengths which can penetrate water, which can be used for bathymetric analysis, like green wavelength. People have used even like the basic sonar technology, which is like a sound-based technique. It's actually not like a satellite remote sensing, but it's a survey method, which is used for like bathymetry analysis. And there are like specific satellites which tell like what is the water elevation level and etc. And remote sensing is definitely useful, but it's not useful for bathymetry of very deep water bodies. The remote sensing EMR cannot penetrate water to like a large extent. For shallow water bodies, it is possible, and for like shallow water bodies, it is also possible to assess what is present underwater. So, if you want to go at like deep lakes, which is like hundreds of meters deep, or ocean, which is like extremely deep, it's difficult to assess the underwater surface from remote sensing or do bathymetry. But for shallow water bodies, it is possible, and people are actually doing it. Is there any thumb rule when data from different projections are being used together for analysis? It's like a complete different field, like data projections. Maybe like with respect to JS, but still, yes, I can answer this. Like when you're using data from different projections, the first thing you should use is take any one data as the base and bring all of the data to the same data projection. Because whatever data you may be using, if the datum is different, like data projection is one aspect, the datum of the data, like with respect to which datum the data is being measured, each data comes with its own origin. Like data means what I say is like the origin point where the x, y, z, 0, 0, 0 is located. Each data set may have a different datum. Similarly, each data may have a different projection. So whatever different data sets you use, always bring them to a same datum, bring them to a same data projection before combining them or using any sort of overlay analysis in JS. If you miss even like converting one data set, one datum or one projection, then the overlay analysis is going to give a wrong result. So there's no thumb rule which projection is better or which datum is better. It's up to us to choose. But all the data sets should be in the same projection. If you want meter based linear measurements, you can go for UTM projection. Or if you want like geographic thing, you can go for like geographic lat long without any sort of like projection. It's up to us to choose. But again, I'm repeating, please bring all the data to sets to common data projection and common datum frame. Yeah. Which models are useful to detect large scale events? NWP models or LiDAR based models? So I think this is also with respect to meteorology. If I like numerical weather prediction, I guess NWP. Not like I'm not an expert in meteorology, maybe, but but I think it depends on like what sort of process you want to model. So I'm really sorry I cannot answer this question to the fullest extent, as I am not like a meteorologist, but basically like working like land surface applications like vegetation and water and so on. So maybe like I'll look at it.
So that is it. These are all the questions which we received in the Q&A sheet.
Okay.
So
Okay, fine.
maybe then we can end the session. Because, if any viewer has any more questions, maybe they can write to us later.
Yeah, definitely. My email is also there in my first slide. They can write to you people, or they can write me whatever. I'll be happy to answer those.
So for now, then we'll end the session.
Yeah, fine, Shiva. You can.
Thank you, sir. Thank you very much for a very interesting and informative session. It was really nice. The videos were really nice. Thank you very much,
Thanks a
sir.
lot, Shiva. Thank you. Thank you. Have a good evening. Yeah.
Thank you. And on behalf of the organizing team, I would like to thank our PhD students Girish, Navinya, and Shravani, who helped us backstage with the viewers' questions. Thank you again for being part of the eSchool today. We'll see you tomorrow with a new topic on climate. Have a good evening and stay safe. Thank you.